Okay, welcome everybody. We're here to review for the final exam. And so this is gonna be the Welty, why am I not working here? Yep, so Welty solutions. There you go. All right, what is the difference between a conductor and an insulator? Give an example of each. So conductor, these have free electrons, right? Electrons that are loose, free to roam around. Whereas insulators hold on to their electrons. Those electrons are bound. And even if you give an insulator more electrons, it keeps those too. So conductor, right, typically metals, like iron, nickel, cobalt are great conductors. So, a metal spoon, a metal plate, good conductor. Insulator, plastic comb, etc. All right, methods of charging. Give an example of each method. So charging by friction, right? We're picking up electrons and transferring them off a surface from one surface to another, for example. You did this with John voltage in the example, even when you scuff your feet along the carpet and pick up electrons. Or another one could be rubbing a balloon on your head, right? Here's our balloon. Why can I not write all of a sudden? Okay, right, rubbing a balloon on your head. There's your head, right? And you take electrons off your hair onto the balloon and make it a little more negative. Okay, great. All right, charging by contact. That was really the best example we did was a fun fly stick, which is negatively charged, and touching it to a metal sphere, and then making that sphere also negatively charged as well, giving it some more negatives. All right, so charging by direct contact transfer of electrons. All right, number 3. Let's move it up, everybody. So we have some problems here with 3 and 4. Right. All right, so sphere of charge 6 microcoulombs is charged by a contact, drawing new charge -2. How many electrons were transferred, right? So we go from 6 to -2. So that's a jump of 8, right? So that means we have a change of 8 times 10 to the -6 Coulomb of charge. So that's how much charge it gained. Or technically -8 because it went from +6 to -2. And what's the charge of every electron? Whoa, don't forget the negative in there, Welty. So -1.6 times 10 to the -19th coulombs. That's how much one electron is charged. So if I divide those out, that's 8 divided by 1.6, or 5. So it's going to be 5 times 10, and then we subtract the powers, right? That's what we were doing. We were taking 10 to the -6 minus 10 to the -19th. Or -6 minus 19, right? And we were getting 10 to the 13th power, right? So that many electrons were transferred in that process. All right, cool. Number 4. Why is this not doing it? All right. It's all about Coulomb's law. And we actually want to do a calculation here. So electric force, K is 9 times 10 to the 9th. So that's just a constant of proportionality to make Coulomb's law work. And then one charge, hey, it's 8 coulombs, so we'll put a little 8 here. The other charge is 2 coulombs, so we'll put a little 2 there. And then they're separated by 4 meters. I see it, and we're gonna have to square that number. Okay, so 8 times 2 is 16. So we're gonna have 16, or actually if we do this out, if we multiply the numbers on the top, 9 times 8 times 2. So 9 times 8 times 2, that is 144 on the top. 144, and that's times 10 to the 9th, by the way. And on the bottom, 4 squared is 16. So if I divide this number out, I'm going to get 9 times 10 to the 9th newtons. All right, I know that's coincidental that it's the same number as the constant proportionality. Totally coincidental. But that's how the math works. Okay, also describe what happens to the electric force between the charges if you make the following changes. So if I double one of the charges, so if I come along and make this 2Q1, so I make it bigger, electric force, hey, it's electric force, don't forget, is directly proportional to charge. So if I double a charge, I'm gonna double the force as well, okay? So force will double as well. I'll write that, force doubles. All right, but what if I double the distance? So I'm going to make these twice the distance apart. So if I go here and make this 2D apart, right, with Q2. So I've moved Q2 over there, right? So here the electric force isn't proportional, it's inversely proportional to distance squared. So if I double that distance, that's going to be 1 over 2 squared, or 1/4 as much force, so 1/4 of the amount of force, okay? All right, that is our static electricity stuff. Onward to current electricity. All right, we'll show these two here. So 3 components of a simple circuit: battery, wires, and light bulb. So our battery, hey, that's our source of energy. So that's where we get our energy from. Hold on, I'm not gonna write source there, but that's the energy for the circuit. Okay, and we know that commonly as voltage, where the definition of voltage is technically the amount of energy per charge, right? 6 volts just means that we're going to give 6 joules of energy to every 1 Coulomb of charge. All right, the wires, oh, we need charges, right? So the wires are where the charges are, right? The wires are good conductors, right? A lot of free electrons in there, in that copper wire, right? All right, cool. Light bulb, hey, that's going to provide our resistance for our circuit. And we know that because we see the electrons give up their energy in the form of light and heat for the light bulb. All right, number 2, series circuit. Game on. So we have a 2 and 4 ohm in series with our battery, that's 6 volts. So total resistance, right, we just straight up add them together, 2 ohms plus 4 ohms, and that's going to give us 6 ohms. For the current, well, hey, we have a 6-volt battery with 6 ohms of total resistance, so that's going to be 1 amp. Okay, and when we get our 1 amp flowing through our circuit, there's our 1 amp, right? All of that current's going to go through the 2 ohm, so we have 1 amp of current going through there, and all of it will keep going through the 4 ohm as well, right? There's only one path to take through our series circuit. Whereas our parallel circuit, there's more than one road to travel, everybody. All right, so let's check that out. So in the parallel circuit below, right, here we have 6 volts, then we have a 2 ohm and a 4 ohm in parallel this time. They were in series before. You know, if I have my current flowing, current's going to take different paths. So let's calculate the total resistance, 4 and 2 in parallel, which means we have to do some inversing here, and that's fine. Oh, not red, well, T. Let's stay blue. So that's going to be 1 over, what, 4 ohms plus 1 over 2 ohms. So I have to do a common denominator here. So that's going to be, what, 1/4 plus 2/4 for a total of 3/4. Right, but remember, that's 1 over R, right? So if I cross multiply to solve for R, I'm going to get 3R equals 4, or R is 4/3 of an ohm, which is 1.33 ohms. Got it. You can do that, prove that on your calculator. All right, so current then, I've got a 6-volt light bulb, or sorry, 6-volt battery, 1.33 ohms of resistance. So if I divide that out, make a better ohms, well, T, no problem. 6 divided by 1.33 is 4.51 amps of current. And so again, when these amps start flowing around, that's 4.51 amps. My 4s are a little funky there, I get it. When they get here, hey, some of those amps can go this way, some can go up here, right? So different amounts of current will go through different parts of the circuit, and then all that current meets up here and goes round and round. All right, number 4, using the definition of current, right, which is charge. So it's how many coulombs flow in my circuit per second. That's what an amp is, if we're talking about units here. So if we have 12 amps of current going through our hairdryer, and how many charges flow in 6 seconds? So it looks like 6 times 12, which is 48 coulombs of charge are flowing. That's a lot of electrons, right? Because remember, 1 electron is 1.6 times 10 to the negative 19th coulombs. Well, negative, that is. All right, cool. Onward to magnetism. Oh, yeah, here we go. Magnetic domains. Sorry, my sketches aren't in there, so we have to draw it by hand. Yeah, what is a domain? Hey, that's a small area in a material where charges are flowing. right? And so if I look at a magnetic material, let's draw in some crazy domains here. How many I'm going to put in there. Fine, each one of those little areas is a domain. So same thing, here's a non-magnetic material. It also has domains too. Okay, so I'll try to make the domains look the same. How about that? It's like making a little map here, everybody. Okay, so in a non-magnetic material, hey, electrons are flowing this way in that domain, this way in that one, this way in that one, this way in that way, this way here, this way there. Right? They're flowing in all different directions, right? So the net result is no magnetism. Like a soda can, it's metal, it's got some free electrons, but it's not naturally magnetic. But if you look at something that is magnetic, that means the electrons in that domain are flowing that way, electrons in this domain, this domain, this domain. All the currents, little currents, they're flowing in each domain are all flowing in the same direction, which gives you an indication of like, oh, where they're flowing is kind of like north, where they're flowing away from is kind of like south, and that makes the material magnetic. Cool. All right, number 2, this is right-hand rule stuff, everybody. So remember back to right-hand rule, thumb is velocity, index finger, pointer finger is magnetic field, and the middle finger, or ring finger, right, is the magnetic force. All right, so if we do that, we say, all right, magnetic field is up, our velocity is towards you, this is coming towards you out of the page here, so that's going to give you a magnetic force to the left. So magnetic force will be to the left, correct? Yep, I just did it. All right, number 2, here we have the velocity is up, the magnetic field is out towards you, that's what the dots mean. So if I do that, see, velocity up, magnetic field is towards me. Hold on. Magnetic field. Oh, so this will be our magnetic force is going to be to the right. So magnetic force to the right. Got it. All right, keep on going. So now we have a problem with that to calculate. So here we've got a 5 Coulomb charge. It's going this fast, 2,000 meters per second to the left in a 4 Tesla magnetic field directed away from us, right? That's how we see the little X there, it means away from us. So what's the magnitude and direction of the force? So we can just calculate it straight up. That's 5 coulombs of charge, and they're going 2,000 meters per second. That's pretty fast. That's not crazy fast for charges. In a 4 Tesla magnetic field. So if I multiply these numbers out, 5 times 2,000 times 4 equals, big number, that's okay, 40,000 newtons of force on our charge, right? Yeah, that's typical. All right, what's the direction? Well, again, I have to do right-hand rule to figure out the direction again, like we just did above. So the velocity is to the right, sorry, to the left. Velocity to the left. Magnetic field is away from me, like here, so that means our magnetic force is going to be down, right? Hold on. Velocity, magnetic field, force is down. Yeah. Correct. So this is going to be down. Oh, downward. Got it. Perfect. All right, number 4. How is magnetic field of the Earth produced, and what does it protect us from? So, yeah, let's draw it in, right? We have our magnetic field lines running south to north here for our Earth. And inside our Earth, right, this is the core, right? That's where the magnetic field's generated. So in the core is molten liquid iron, right? And iron is a great conductor because it has tons of free electrons, right? And you get our Earth spinning and rotating. So that electricity in the core of the Earth, once I get it moving, is going to produce magnetism, and hence our magnetic field. Okay. What does it protect us from? Well, hey, the sun is here, right? And the sun sends streams of particles towards us called the solar wind. And when those solar wind particles hit the Earth's magnetic field, they spiral around it and safely dive into the Earth at the poles, where none of us really live. So that keeps us protected from solar radiation and space radiation in general. Cool stuff. Thanks, Earth's magnetic field, for protecting us. All right, on to waves. Sketch a diagram of a transverse wave and label its characteristics of wavelength and amplitude. I can do that. Well, you can do that too. All right, so here's a transverse wave. Oh, we're sticking with red, I guess. That's cool. All right, wavelength would be from crest to crest or trough to trough. There's our symbol for wavelength. An amplitude, if I bisect this here, I'll draw it in there, would be half the wave height. All right, cool. Going back to blue. So number 2, I observed 20 waves passing by in 10 seconds. The distance from crest to crest is 3 meters. So what's the frequency, period, wavelength, and velocity of the waves? All right, frequency by definition is waves per time. So I'm gonna say 20 waves over 10 seconds. So that's gonna give me a frequency of 2 hertz. Got it? Period is just the inverse of that. It's the time per wave. So 10 seconds over 20 waves. Or if remember, it's just the inverse of frequency. That's going to give me half a second to see one wave, right? All right, crest to crest is about 3 meters, they say. So crest to crest, hey, that's just the wavelength straight up. All good. And then remember our wave equation. Velocity is frequency times wavelength. So frequency is 2 hertz. The wavelength is 3 meters. So I have velocity of 6 meters per second. All right, hopefully that was easy. All right, number 3, identify the wave behaviors. Oh, here we have a wave coming in towards a barrier at an angle, and it leaves the barrier at the same angle. Oh, that's called reflection. Perfect. All right, here we've got a wave, nice and straight and plane waves, and it goes through an opening between barriers, and it starts to curve. That is called diffraction, where the shape of our wave is changing. Of course, that is dependent on how big the opening is and the wavelength. Here we have a positive pulse coming at a negative pulse. Dun, dun, dun. Oh, and then I see no wave for a moment. Thus, it's destroying itself, so that is destructive interference. Got it. All right, last couple problems here, I think. Oh, last one, number 4, perfect. So third order standing wave is shown, right? Because I see one antinode, a second antinode, and a third antinode, which are produced by constructive interference. And we got 4 nodes, 1, 2, 3, 4, which are produced by destructive interference. Well, let's write those down because we'll just remember those, right? There's an antinode, and then here are nodes, right? These are nodes, just so we remember the characteristics. And it says, distance from end to end is 9 meters. So it's 9 meters from here to here. I got it. Okay, and it's producing 400 vibrations in 20 seconds. So that sounds like a frequency thing, right? So frequency, 400 waves in 20 seconds. So that's going to be 20 hertz, right? Perfect. All right, wavelength of a standing wave. Remember, by definition, it's node to node times 2. So wavelength is node to node times 2. All right, so node to node distance, well, if this is 9 the whole way, then what's node to node? Well, hopefully you recognize that that's going to be 3 meters, right? 3 meters from node to node, right? Because 3 and another 3 and another 3 give you the total distance of 9. All right, so that's node to node times 2, so that's 3 meters times 2, or 6 meters for wavelength. If I want to know the velocity of these waves, again, it's frequency times wavelength. So that's going to be 20 hertz times 6 meters, or 120 meters per second. Woo! All right, we did it, everybody, in under 20 minutes. All right, don't forget, the last page are your choices for what you want to do here. You know, your example, are you going to do polarization of charge or electromagnetism from your digital portfolio? So go back and choose an example. And same thing here with your term 4 project. Hey, what are you going to do? Diffraction or refraction from that. All right? Put in a great effort studying and take care.